In this video, I will derive the vibrational entropy given the vibrational partition function. When a system consists of distinguishable particles, its entropy is equal to nr times lnq plus dlnq over dlnt. N is the number of moles of the particles. R is the gas constant. Q is the partition function of all particles, and over here we are talking about a derivative. This is the first derivative of lnq with respect to lnt. Q is the total partition function, T is the temperature of the system. And Q is the product of the translational, rotational, vibrational, and electronic partition functions. Therefore, lnq is the sum of these four logarithms: translational, rotational, vibrational, and electronic. So if we plug in the sum of these four terms in here, lnq, and here, we will see the entropy of the system is the sum of the translational entropy, rotational entropy, vibrational entropy, and electronic entropy. What if the particles are indistinguishable? Then we need to divide the total number of microstates by n factorial. This is because when we have n particles occupying different energy levels, there are n factorial permutations that correspond to only one possible arrangement of these particles. So we need to divide the number of microstates by n factorial. Alright, therefore we have a different expression for the entropy of a system that consists of indistinguishable particles by adding this correction, minus Boltzmann constant times the natural logarithm of n factorial. And over here we need to use Stirling's approximation. Ln n factorial is simply n times the natural logarithm of n minus n. And then we can combine these terms. The result is this. Again, this is the equation for the entropy of a system that consists of indistinguishable particles. And now we can plug in this lnq equals ln q trans, q rod, q vibration, and q electronic to here to compute the total entropy of the system. Now what about this correction? This correction is often included in the calculation of the translational entropy. And it's included only once. Again, we should not double count the correction, therefore we just include it once in the calculation of the translational entropy. So why don't we include this term in the rotational or vibrational entropy? It's simple because sometimes you are looking at the entropy of atoms. And atoms do not have rotational energy levels or vibrational energy levels. Therefore, they do not have rotational partition function or vibrational partition function, and therefore there's no rotational entropy or vibrational entropy for atoms. So it's more convenient to include this correction in the expression of the translational entropy. So let's look at now the vibrational entropy. First, the partition function is this. We can derive this, and I derived this in a different video. So this h nu is Planck constant times the frequency of an harmonic oscillator. For example, HCl, we can approximately use the harmonic oscillator model to describe the oscillation of the HCl molecule. What is beta? Beta is the reciprocal of kBt. So if you know what the temperature is, just plug it in, you can compute beta. What about the vibrational entropy? The vibrational entropy, again, it's nr times lnq plus dlnq over dlnt. We just need to put this vibration in the subscript. And then we plug in this expression for the vibrational partition function in here and in here. Now we have a really complicated expression here, all right, but this can be simplified. First, this part. It's really easy to see the logarithm of a division is simply this guy minus this guy. And also, we know the logarithm of e to the power of something is that something. So we have negative half h nu beta here minus the logarithm of this 1 minus e to the power of negative h nu beta. So we dealt with the first term here. It's expanded in this one. And now, by looking at this expression, it's a little complicated, but first we can replace this d ln t with negative d ln beta. Okay, so pay attention to the sign change here. This is a negative sign here, and on the bottom it's d ln beta instead of d ln t. And why is that? It's very simple, because beta is the reciprocal of kbt. So d ln beta is d ln 1 over kbt. It's negative d ln kbt. And this is the sum of ln kb and ln t. ln kb is 0. I'm sorry, the exact differential of ln kb is 0 because ln kb is a constant. The exact differential of any constant is 0. So we have this d ln beta is equal to negative d ln t. That's why we have this negative here, and we replace this d ln t with d ln beta. All right? So basically, it's equivalent to this. The exact differential of 5 over x is the exact differential of the logarithm of 5 over x is equal to the exact differential of ln 5 minus the exact differential of ln x. And the exact differential of ln 5 is 0. All right, get back to this expression. Also, we know this equation holds true always. It's because the first derivative of ln beta is 1 over beta. Therefore, d ln beta is d beta over beta. So we're going to plug this into here. D ln beta is d beta over beta. And then we got this expression. It looks even more complicated, but we can simplify this. We can simplify this. So what about the top here? The top here is from, again, here. I just replaced this guy with d beta over beta. Okay, again, this guy is d beta over beta. So this beta appears here because you have d beta over beta on the bottom. Therefore, I just flipped this beta up. Now, let's look at the first derivative of this term. This part is simple. It's just negative half h nu, and we have negative half h nu times negative beta, so we get positive half h nu beta here. Now, what about this one? We have negative sign here, another negative sign here, so I'm going to replace this two negative signs with a positive sign. So this term becomes plus beta times d ln this guy over d beta. Fortunately, this part and this part cancel. You have negative half h nu beta, you have positive h nu beta that cancel. So we have only two terms left, this term and this term. All right? So how can we go from here to here? Well, it's very simple. In calculus, we learned the chain rule. So we're taking the first derivative of the logarithm of function. Therefore, we have 1 over that function here times beta, of course. We don't forget about the beta here. So it's 1 over that function multiplied by this beta. And then we need to take the first derivative of that function over here. What's the first derivative of this function? It's very simple. Again, chain rule again. The first derivative of 1 is 0. The first derivative of this exponential function is going to be negative h nu times this same function. Negative h nu times this negative sign is positive h nu. So you see this positive h nu here times this exponential function. Okay. And then we further simplify this equation. We put this h nu and beta together, and we have this h nu beta here. And now you can see this vibrational entropy is a function of temperature. You see this beta is the reciprocal of 1 over kBt. So you see beta here, beta here, beta here, and beta here. But also you can say, well, why don't we say this vibrational entropy is a function of h nu beta? I mean, we can define a new variable. It's h nu beta, h nu beta, h nu beta, h nu beta. And what is h nu beta? H nu beta is simply just h nu over kBt. And now let's look at HCl. For HCl, the wave number is 2,900 inverse centimeter, and we can use hc over lambda to compute the corresponding energy, and we'll see this h nu over kBt for hydrogen chloride is roughly 14 at the room temperature, and this is actually a big number. 14 is a big number because if we think about e to the power of negative 14, that's negligible. So for HCl, this exponential function is a very, very small positive number. And therefore, 1 minus such a very, very small positive number is roughly 1, and ln1 is 0. So we have a 0 here. And again, when this h nu beta is equal to 14, we have 14 here times e to the power of negative 14 over 1 minus e to the power of negative 14. So the bottom is close to 1. E to the power of negative 14 is very, very small. Times 14 is still very small, so this term is very close to 0 as well. So again, for this HCl molecules at the room temperature, because h nu beta is large, it's approximately 14, I believe. You can recompute this. You can just plug in the wave number of HCl, which is 2,900 inverse centimeter, into this hc over lambda over kBt. You can get this number. It's, I think, roughly 14, and you get this e to the power of negative 14 approximately 0. Therefore, the vibrational entropy of HCl molecules at the room temperature is roughly 0. It's understandable because at the room temperature, most HCl molecules occupy the ground vibrational energy level. So there's roughly just 1 microstate. And then the entropy is roughly 0. Now, what if we have a very high temperature? If the temperature is high enough to make this h nu beta small enough, let's say this h nu beta is now much smaller than 1. For example, if you have a high temperature, and if you have, let's say, bromine to gas, because bromine is so heavy, the bond between two bromine atoms is so weak, and then it's possible to have a small frequency, vibrational frequency for the bromine molecule. And also, if the temperature is high enough, then we can have a small h nu beta. In this case, we can expand this exponential function to 1 minus h nu beta. This is the so-called Maclaurin expansion or Taylor expansion. And after we do that, we can plug in this equation in here, and also in here. If we do that, we can simplify the expression for vibrational entropy. So first, let's replace this exponential function with 1 minus h nu beta here. And it's going to be 1 minus h nu beta. Therefore, we have this just logarithm of h nu beta. And we can plug this equation in here. So 1 minus e to the power of negative h nu beta is just an exponential function here. And we just plug it in. We get this h nu beta on the bottom now. It's also on top. Therefore, this h nu beta cancels with this 1 minus e to the power of negative h nu beta. All right, and then we have just this term left. It's right here. And then we have a simplified expression for the vibrational entropy at very high temperature. And also, at a very high temperature, this h nu beta is small. Therefore, this exponential function is very close to 1. And then this is even more simple. This is just nr times the logarithm of kBt over h nu plus 1. So look, this is actually the vibrational partition function at very high temperature. All right? And this comes from the first derivative of ln q with respect to ln t at high temperature. So again, at high temperature, very high temperature, the vibrational partition function is just kBt over h nu. So you're looking at ln q here. for high temperature cases. All right, and how does this L and Q depend on L and T? Well, the dependence is just 1.